Hello, this is Jack Jackson. Today we're going to be looking at a series of videos that are going to summarize some things that we found out about transformations of relations and symmetry with respect to those transformations in some of the projects that we've been working on. And of course we can apply these to the homework exercises as well. Recall that transformations are really our functions themselves that take each pre-image point of a plane and send it to an image point in the plane. And we're currently concerned with the effect of transformations when we restrict our attention to transformations and see how they affect points from relation, both individually how they move points and then collectively how they move the points. And so transformations, one way to think of it is a function that takes a function as an input or a relation as an input and that gives you a new relation as an output. So it's new from old. And this new relation is very similar to the original relation. In the summary notes that we've got below, and this file contains the summary notes for all of the transformations we're going to be studying this semester. And it will describe the changes in the formula, the table, and the graph due to several standard types of transformations. And we'll illustrate each of these with two examples. Probably one will be using a base function of y equals x squared, and the other one will use a base function or pre-image function of y equals x cubed. And then we may also look at one that's not in the notes where the basic function or pre-image function is y equals square root of x. So in the summary notes we'll describe changes in the formula, table, and the graph. And we'll see what happens with each of those things. The tables are lined up in such a way that pre-image and image points at the individual point level are lined up. So we see the pre-image and image on the same line in the corresponding tables. We have a one-page table summarizing all the transformations at the end of the notes. And in general, remember that we found that the formula is backwards from the actual change in the table and the graph, in the sense that the inverse operation is applied. So, for example, if you replace x by x plus 2, what we really do is add 2 to the x's in the table. A fixed point of a transformation is an individual point whose image is the same as the pre-image, so that transformation doesn't change. And when we have a relation, or a set of points, for which a transformation, that should say, collectively maps the pre-image set of points to the same image set of points, even though not all the individual points may be fixed. So the points are moved around, the table's moved around, points are moved around the graph, they're moved around the table, but when the dust settles, collectively, if all the points are the same as the original, just the table's in a different order, or the points have moved around, but ultimately we have the same formula, the same, if we simplify, and the same table and the same graph, collectively, then we say that the transformation is symmetric with respect to that transformation. The relation is symmetric with respect to that transformation. So we're going to break this apart into a series of hopefully fairly short videos. This one's going to talk about translations. So we'll start with the horizontal translation. If we replace x by x minus h in the formula, we've seen that this we'll leave the y values alone, and we'll actually add the constant h to all the x values in the table. Notice the minus built in the x minus h. So the graph is translated horizontally by absolute value of h units. It's going to go to the right if h is positive and the left if h is 0. Technical term for this is called a translation. You might also use the word slide, shift, scoot, something like that. But the technical term is translation. So looking at some examples here, you see y equals x squared. Okay, let's go back. There we are. Y equals x squared. And y equals, in parentheses, x minus 5 squared. So if you can see that we've simply replaced the x by x minus 5 and left the y's alone. So what we're going to do is we're going to actually add 5 to the x's and leave the y's alone. And notice I've done this in such a way that these tables line up, so when I did this, the y values are the same in both. So they're lined up image and pre-image like this. So they have the same y value, but the x is different. How do I get the x? I took the original x and added 5 to get the new one. So negative 4 plus 5 is 1, or 1 plus 5 is 6, or 3 plus 5 is 8. But I left the y values alone. Of course, this must work in the formula. Let's take this and look at it like 8, 9. Plug in the red formula here. 8 minus 5 is 3. 3 squared is 9, and so it does work. Why is the formula backwards? Well, you can kind of see it here. Because what we're going to do is we're composing with the inverse of what we want really to happen. We want to go to the right 5, so we have to add 5 to the 8. But then we need the inverse operation, x minus 5, to take us from the 8. Do the x minus 5 first, that sends us back to 3. Then we do the original relation that says square it, that takes us to 9, and that's ultimately the same as the output over here. And of course, what does that do? That gives us, if you see the graph, the original graph down here is in blue, y equals x squared. We've looked at that one several times. And the new relation is in red, and it is just shifted to the right 5 units. And you see I put a couple of vectors in there, arrows showing how certain points are moved. For example, this point here, 3, 9, goes to the point 8, 9. That's one of the ones that I have right here by this arrow. Or the origin, which is actually the minimum there, also called the vertex, 0, 0, goes to 5, 0. So the vertex or minimum has been moved over to now 5, 0. In fact, every point has just been moved straight to the right 5 units. Similarly over here, if we replace y equals x cubed by y equals parentheses x plus 6 close parentheses cubed, notice that we've replaced x by x plus 6, and we've left y alone. So we're subtracting 6 from the x values in the table, leaving y alone. So again, I just made up a bunch of x's that I was interested in looking at, used the formula y equals x cubed to find the corresponding y's, just like I did use the formula y equals x squared over here. And then from going from the green graph to the purple one, I'm leaving the y's alone so that I can still line up pre-image and image on the same line. But what did I do to the x values? I'm actually going to subtract 6 from the x values, leave the y's alone. So 2 plus 6 is 2 plus a negative 6, or 2 subtract 6 is negative 4. Or 0 minus 6 is negative 6, or negative 2 minus 6 is negative 8. Negative 3 minus 6 is negative 9, and so forth. And as you see, every point is shifted directly to the left. So if we take the point 1, 1 here, for example, it goes to the point negative 5, 1. And you can see that illustrated by this orange arrow here. So everything is going straight to the left 6 units. I also have another one here, I think, at negative 2, negative 8, and now it becomes negative 8, negative 8. So that's shifted from here over here, illustrated by that orange arrow. The orange arrows in these graphs are really not actually part of the graphs. They're just to help illustrate what's going on. Well, if replacing x by x minus a constant gives us a horizontal change, then it stands to reason if we replace y by y minus a constant, that gives us a vertical change. Of course, after all, x is the horizontal variable and y is the vertical variable, and sure enough, that's exactly what happens. If we replace y by y minus k in the form of the relation and leave the x values alone, that's all we do, then we leave the x values alone and add k to all the y values. And the graph is translated vertically. Again, if k is positive, goes up, k is negative, goes down, but that's with this built-in minus in the formula right there. So where it says y minus k, okay, so that built-in minus means that you're actually going to see the opposite sign. So again, the formula is backwards. So if you see it written this way, going from the blue graph to the red one, or blue formula to the red formula, I have y equals x squared as my original. And in the next one, the way it's written on the first line there, you'll see it written as y minus 3 equals x squared. If you write it that way, then you can more clearly see that it's y that has been changed and not x. x has been left alone. So the right side's been left alone, and we can say that the equation has been changed, or equation or formula has been changed by replacing y by y minus 3. So in the table, we're going to leave the x values alone, but what we're going to actually do is add 3 to the y's. So when I look down here at my table, I'll see a table for y equals x squared. Just interesting points. I might be interested. There are actually infinitely many of them. I just picked a few. And I've lined this time up so that the x values here are the same as the x values here. So that's going to line them up pre-image to image. And this time, the x values are staying alone, and the y values are changing. Therefore, each point is going to stay with the same x value. It's not going to move horizontally. It's only going to move vertically up and down along that vertical line. And we actually add 3 to the y's. So, for example, there you see 4 plus 3 is 7. 1 plus 3 is 4. 9 plus 3 is 12, and so forth. And we have lined these up pre-image and image point, and that's what these little arrows are indicating, is that these are at the point level. We have a pre-image on the left and the corresponding image on the right. Similarly, if we have, well, let's see what that does, of course, to the graph. Well, that's just going to shift it up 3 units, and so everything goes straight up from the blue graph to the red graph. The whole thing is just shifted straight up. Here's one where we shift down. Y equals x cubed is our pre-image relation. It's our pre-image formula, our pre-image table, our pre-image graph. And then if we replace y by y plus 2, then we really subtract 2 from the y's, but we leave the x's alone. So notice again, the table's set up so that the x's are exactly the same going across, but when you go across on the y's, the new y's are 2 less than the original y's. And you can check that by plugging those in. For example, let's plug in this one here. Plug in -2 for x. -2 is cubed is -8. And then you plug in -10 for y. -10 plus 2 is -8. -8 equals -8. It checks. Now, if you're going to put this in your calculator, instead of writing it as y plus 2 equals x cubed, you'll have to write it as y equals x cubed minus 2. If you encounter it as y equals x cubed minus 2 to start with, which is definitely very possible, then I think it's more useful to think of it as y plus 2 equals x cubed. So even if you just do it in your head, or you could write it down, rewriting it as y plus 2 equals x cubed, I think, makes it easier to see that the x's were left alone and it was the y's that were changed. Also, writing in that form, you can think of it as the formula is replace blank by blank. In this case, replace y by y plus 2. If you write it that way, then the formula is always backwards. Okay? So, instead of adding 2 to the y, you're really going to subtract 2 from the y's. And of course, that's going to shift the graph straight down 2 units. And you can see that, and it's kind of illustrated by those arrows going down straight 2 units. So in general, a translation is done by a vector, say a vector hk. If we want to translate by a vector hk, we can just think of that in 2 steps, a horizontal translation and a vertical translation. So if we replace x by x minus h and y by y minus k in the formula for a relation, then we end up adding h to the x coordinate of each preimage point and k to the y coordinate of each preimage point to find the coordinates of its image, and the graph is translated by the vector hk. So again, we'll use y equals x squared, same table as before, for an example. And here I've written it as y minus 3 equals parentheses x minus 2 close parentheses square. We see that in the formula we replaced x by x minus 2 and y by y minus 3. So in reality, what we're going to do is the opposite. That is, we're going to add 2 to the x values and add 3 to the y values. Okay? And what that's going to do is shift it. Okay? And which way is it going to shift it? Well, let's take a look here. So now they're lined up so that I'm adding 2 to the y, 2 to the x, and adding 3 to the y. Check that out. -4 plus 2 is -2. 16 plus 2 plus 3 is 19. -3 plus 2 is -1. 3 plus 9 is 12. 3 plus 4 is 7, 3 plus negative 2, or 2 plus negative 2 is 0, and so forth. Okay, so that means every point is going to be shifted by the vector 2, 3, which means it's going to the right 2 and up 3. And so I've got these vectors right here are the vectors they are the vector 2, 3, two copies of that vector. That's the vector that goes right 2 and up 3. And you can see that every point is moved to the right 2 and up 3. This one over here has been shifted by the vector negative 5, negative 2. In other words, left 5 and down 2. You can see that by these vectors, negative 5, negative 2 here in orange. And we can go back up and see that in the table. What means, so the vector's not backwards, it's in the right direction. So we're really going left 5, we're really going down 2, we're really adding negative 5 to the x, we're really adding negative 2 to the y. So if we add 5 to 2, we get a negative 5 to 2, we get negative 3, and add negative 2 to 8, we get positive 6. So there's a pre-image and image pair, and the vector going from the point 2, 8 to the point negative 3, 6 is the vector negative 5, negative 2. Now, of course, the formula is backwards. In the formula, we're going to be replacing x by x plus 5 and y by y plus 2. And so, since we start with y equals x cubed, we end up with y plus 2 equals parentheses x plus 5 close parentheses cubed. And if we want to solve for y, we can by adding a negative 2 to both sides and see it written in that second form. So, these are general translations. So, a couple things here. Defining parameters. Notice that a general translation requires that we define a vector by which each point is transformed, and then we can think of that vector as, two components, a horizontal change and a vertical change, and we think of that as two parts to our transformation. When we translate something, we're just sliding this thing around, and so any pre-image point is going to go to what we call a congruent image. So the image is the same size and shape and orientation. It's just moved around. So all distances, corresponding distances, are congruent. So if you have a distance between two pre-image points, let's say the distance from 0, 0 to 1, 1, which is square root of 2, then if you take the distance from 2, 3 to 3, 4, also same distance, square root of 2. Distances are all preserved. Also, angles are preserved. So if you take the angle from negative 1, 1 to 0, 0 to 1, 1, which is actually a right angle, then you're also going to get a right angle when you connect up their image points. So whatever size an angle is, then you're going to get the same size angle from the pre-image to the image. Okay? Fixed points. Doesn't have any. Every point is moved for a translation, so it has no fixed points. You can, however, have translational symmetry, but we're not going to really look at this too much, but I will give you one example. If you translate take a line and translate it so that it is the vector goes along the line, then it does give you the same line back, so that would have a translational symmetry. So, for example, if you take the line y equals x, the vector 2, 2 basically goes along the line. And so points like 1, 1 would go to the point 3, 3, which is also still on the line y equals x. And because the line goes on forever in both directions, that's going to be a requirement if it's going to have translational symmetry, because every time you move a point, there has to be another point to come take its place. And since every point is moved, we're gonna need that. Okay. And so, for example, you can see that in the formula. If you translate by the vector 2, 2, you're replacing x by x minus 2 and y by y minus 2. So y equals x becomes y minus 2 equals x minus 2, but that just simplifies to y equals x if you add 2 to both sides of the equation. Now, if you ever take a course in trigonometry or pre-calculus, you do study a lot of functions there that have a horizontal symmetry. Let me give you an example here. There's a function called sine x that you study there, and it turns out to be a wave. And since this wave goes on forever, if you shift it by the right amount, and it turns out the right amount is 2 pi, so if I say minus 2 pi, this new graph is going to be the original graph shifted to the right 2 pi units, and if you look, it just lands right on top of itself. And so this has a translational symmetry that's horizontal. Functions like this with this horizontal translational symmetry are called periodic functions. Alright, now let me just do a few more things here with a couple of different programs. First, with Graphmatica, I'm going to use an example to get us started with, and this is x squared plus y squared equals 1. That's actually going to be a circle centered at the origin of radius 1. Now let's see what's going to happen when I replace x by x minus 4. What's going to happen? Okay, hopefully you said it's going to be shifted to the right 4 units. Now what if I go back to the original and replace y by y minus 3? How about y plus 3? Well, that's going to shift down 3. What if I do both? That'll shift to the right right 4 and down 3. So that shifts by that vector 4, negative 3. So you can see these things shifting around. I also want to look at this. This is a GeoGebra sketch that I file that I put together. This is an exploration that's in Blackboard posted for you. And in this particular sketch, you can type in a formula in this box here, B1. This is in the directions. And I've typed in the formula x to the 1/2 power. So y equals x to the 1/2 power is graphed. It's actually graphed over here in black, but the red graph is on top of that, which is the same graph. And I can, by manipulating h and k, I can translate this by the vector hk. So notice as k changes, this graph is shifted left or right. So let's let k be 2, h be 2, for example. And notice that we have in here pre-image point and image point. And you can set up a table to examine these pre-image and image points. Okay, let's see if I can get to the table a little bit better. There we go, there's a bunch of points. And here I have a bunch of points here. Now I can go here on these pre-image and image points. I can type in whatever I want in these cells right here. I happen to pick some perfect squares so we get some nice integer values for the pre-image points. Whatever you type in these cells, then these points will have the same x's, and the y's will be determined by this formula up here. Okay, so those are pre-image points. They're on the original graph. And the B13 actually is the point that's in B13. That's 1, 1. And B14 is the one in B14, which is 9, 3. And we have the origin here in B12, so it's labeled as B12. Now, okay, and notice that the image point, then, since I've got h is 1 up here, or h is 2 in my slider, I can control that, and now what I'm doing is I'm adding 2 to the x. So I'm shifting by the vector that takes me 2 to the right. And notice here's the formula. It's got some sort of unnecessary 1's in there, but it's y equals x minus 2 to the 1/2 power. Or in this case, the blue one here would be the same. If I want the blue graph to show up, I can right click on this, I think. It's not going to allow me to turn it on and off with this. In my original, I could turn it on and off, but not in this particular Java applet for it. So, but if it's just the translation only, you can see it there. It's y equals x minus 1/2 square, which is, or x minus 2 to the 1/2 power. That's what I have here. Okay, now, so as we change h, we can see this thing sliding around. Now, as I change k, what's going to happen? It's going to now shift up or down. So let's let h be 2, if I can get it back there again. I can also, once I got that point selected, I can use my left or right arrows. And notice it's going up or down by a tenth. And let's say we make this -3. There we go. And so now we're shifting by the vector 2, -3. So that's right 2 and down 3. And you see every single point, if you take an image point like B13, right 2 and down 3 to get to C13, its image, or B14, right 2, down 3. Okay? And of course we actually can figure out what those are. B14 is the point 93. If you go right 2 and down 3, you're adding 2 to the x and subtracting 3 from the y. That gives you 11, 0, and sure enough that's the coordinates there for C14, its image. What's the equation? It's y equals, it's in the red here, y equals x minus 2 to the 1/2 and then minus 3. Now we wanted to really probably think of that as y plus 3 equals x minus 2 in parentheses to the 1/2, but then if you solve for y, then you're going to get the version that you see here. And so you can see those translations. So there's a introduction to translations. Come back for the next video and we'll talk about some other transformations at that point.